Hi guys, welcome to the Fluid Static lecture video with me, Dr. Shida. On this video, I will continue from where we left. Last one, in part 1, we did on manometers, where you calculate pressure from the difference of height in manometers. And for this video, we will continue on part 2, where we going to learn on hydrostatic forces. This will be hydrostatic forces. I'm just practicing my writing here. Okay, hi guys, what's up? I know staying home until this global pandemic is over is hard. May everything will go back to normal soon. This will not be like our video lectures as our usual lectures. I hope that all of us are able to adapt with this method for now. Thank you for your cooperation, guys. So for your information, I will try to make these video lectures for 10 minutes every part. So it's easy for you to fast forward or return back to any part that you are missing. Or you can ask me directly if you need any more clarification. Okay, let's go on hydrostatic force. What is hydrostatic force? So hydrostatic force happens when you completely immerse anything, an object or yourself, underwater. Okay, so if you have a tank and then you have a water, you can have an object here or a diver swimming. Everything underwater will be completely subjected to fluid pressure. Okay, let's see. So at rest is subjected into fluid pressure. Okay, so go back to this. Any kind of object, any shape, subjected to pressure. So from this pressure, we can calculate, like for engineering application, you want to calculate how much force is actually acting on these people here or the object there. So we can do this by for simplicity, let's look at this diagram where you have a lot of parallel forces acting on it, right? So this forces of pressure is a distributed load. It is very small or none at the top surface, but it keeps increasing as it reaches the bottom. So this is your fluid pressure, okay, or hydrostatic force. Hydrostatic forces acting on the surface. Okay, so for a plane surface, so for your for this topic, we will calculate on plane surface. Okay, and then we can determine the force, and then we can calculate the center of pressure where it is actually acting on the plane surface submerged underwater. Okay, let's take a look at this dam here. We know that dams are built. If you walk over the dam, you can see the walls are very thin at the top and it gets very thick as you go to the bottom. This is because as you get to the very bottom of the dam, the pressure is really high, so it needs very high thickness of the wall so that it can sustain the load without breaking apart. Okay, for plane surface, when we want to calculate hydrostatic pressure, we have for vertical ones, this is vertical, so we will have this increasing load as you go down the height, and we have a flat or horizontal surface, or we have an inclined surface. So see this. This is the resultant hydrostatic force acting on the plane. They are all perpendicular to the surface. So it is actually 90 degree. All of them. So this one will be 90 degree. Okay, this is for curved surface. So we learn that pressure is rho g h, right? What is rho? Is your density of fluid. We have g is your gravitational acceleration, or 9.81 meter squared second. And then we have height, which is your height, the height of water. Okay, so we were talking about hydrostatic force, right? Hydrostatic forces. Hydrostatic forces, this is force, so it's F. This is pressure. How do we get forces from pressure? We can do that by looking on another popular equation for stress or pressure. Is P equals to force over area. So if we arrange this formula, you will get it's F equals to P times A. So we have P equals to rho g h, and then we have F equals to PA. P is this, right? So it becomes rho g h times A, and you will get your force or hydrostatic force. A is the area where it is in contact with fluid at rest. Okay, so area is, we know, is length times width, right? So it should have length, it should have width. So you get this formula, F equals to rho g h A, which is this formula here. So let's say I have a flat object, and then which have the length and width and thickness. I put it flatly in a tank here, right? So that is your L, that is your width, and it has a lot of pressure acting on it. Okay, so we can calculate the resultant force there. We can calculate it to get Fr. Okay, this is the method we use to analyze hydrostatic forces. Okay, we know that it is perpendicular to the surface. So if you have the vertical or horizontal, okay, incline, our force will be 90 degree to the surface. Okay, always 90 degree. Okay, and if it's in vertical or in incline, the pressure will varies linearly with depth. So for vertical, you have something like that, right? For horizontal, no, because it all on the same height, so same amount. But for this one, you will have the same effect of height. And then all this, it will go to the center of pressure. The center of pressure is where actually the hydrostatic force is acting. Okay, we know that we have hydrostatic pressure in water. In water, we have hydrostatic pressure, and on the surface above the water we will have PATM. So for the sake of simplicity, we can remove PATM. We just try to analyze our hydrostatic pressure, which is happening only in the water. Okay, for first case, we have horizontal surface. FR will be acting at the centroid of the surface, which is in the middle, right? On a surface of area, like I said, this is the side view, so your area will be area of surface is A times B. You don't see A because B is that way. Okay, if I draw it back, this is your flat object, this is your A, that is your B. Okay, because this is horizontal surface, everything is on the same height, so your magnitude of forces will be the same. Okay, so how to calculate it? How to calculate your force is we use formula. Force equals to rho g h a. Okay, rho is your density, g is your gravitational acceleration, h is your height to the surface, this is your P component, right? Pressure component, your pressure. A is your A times B, so you get rho g h a b, which is this. Okay, for vertical surface, you can see that we have a pressure that varies linearly with depth, right? So we have these parallel forces which increase in magnitude as it goes to deeper. Okay, so in this case, you see that your object is completely submerged underwater, and then there are excess water on the top. So we need to consider the remaining height to the surface. Okay, so same procedure. The pressure where it is acting is at the centroid, so it should be your PC will be sorry, not your PC, it's your PC will be your B. Your H will be B over 2. So when we do the formula, so when we do this, is pressure equals to rho g h a. Same formula, rho g h is your pressure, your area is the same, A times B. However, for your height, you should know that it's only acting half of the height, so it should be rho g b over 2 times a times b. Okay, this is because why do you see on this equation we have s, on this equation we don't have? So this is because, okay, let me just cancel that, then I cancel this one. It's because of the remaining height to the surface, because our object is further beneath the surface, so we need to, the height there, it should be from here, from the top. So height is equals to s, and then here it only acting half, so it's plus b over 2. So you get rho g s plus b over 2 times a plus times b. So you get this formula, rho g s plus b over 2 ab. Same. Okay, for the exercise part, I will see you on the second part of the video. Okay, on the next video. See you later. Bye.